Hi everyone, and hope you're all fine. So let's discuss about another topic in the series of operating system. Today and the next lecture I'm going to discuss process scheduling. So process scheduling 1 is discussed today, 2 next lecture, and we wrap up the topics in this unit. What we discussed last week on the last lecture, we talked about the process, and we said that the process is a unit of job in computer systems. Also, we discussed the structure of the process, which is called process control unit. We said that it's got a static part and dynamic parts. Static part, we have the resources for a specific job in the computer. And we have dynamic part, as you see here, which execute the program there. Also, we discuss about this dynamic part, which is the thread. And also we introduced the multi-threading concept in the computer. We discuss each part, the structure of each of them, the task, which is here, and the thread. We discuss different fields in these data structures because they are data structures. We can recognize them by the data that they have. Also, we discuss run and wait status for the thread. We said that if the thread want to be executed, they should go to the run state, and if you want to stop them and put them in other queue, we say that they've got to go to the wait state. So to change the state from run to wait to run, we use a function which is called context switching. And at the end, we discuss if you have multiple threads in a process, which one should be executed first. We discuss about the thread scheduling. But today, I'm going to talk about the whole process or process scheduling. We have different processes and we want to see which process should be executed first. So, CPU scheduling. CPU scheduling is the basis of multi-program operating system. By switching the CPU among the processes, the operating system can make the computer more productive. Look guys, if you want to have a multi-programmed operating system, if you want to run multiple programs on a machine at the same time, there should be someone in the computer to give CPU time to different processes. So if you have a CPU scheduling, if you have a plan for the CPU that which process should be executed first, which one next, in that case, you can run multiple programs on the machine. Don't forget that we are talking about single CPU. If you have multiple CPU, the story is different. Multiple cores are way more advanced and the story is different. But here we want to just talk about and introduce the concept of CPU scheduling. So in a single process system, only one process can run at a time. Others must wait until the CPU is free and can be rescheduled. The objective of multi-programming is to have some process running at all times to maximize CPU utilization. So guys, if you have one CPU and each time CPU can execute one process, you cannot have multiple processes on execution. One process at one CPU each time. So this is the CPU scheduler's job to give the right process to the CPU to be executed. A process is executed until it must wait, typically for the completion of some input-output request. So when you give a process to the CPU to be executed, we need to, in most of the time, we need to wait for the CPU to execute that process and then terminate that, or we may need for get some input, for example, from the user. So we need to wait for that. These are the different status of the process that we will discuss them later. And this is CPU scheduler job to actually identify the differences between them, termination, waiting, and request for input-output, to put the right process into the CPU. So, because we are talking about the multiple programs, we have a lot of processes which are kept in the memory at one time. When one process has to wait, the operating system takes the CPU away from that process and gives the CPU to the other processes. So this is the whole job of process CPU scheduler. So to give one process to the CPU, and when one of the processes finished, and take it away from that. Or it's got to wait for an input output, put it in the wait queue, and give CPU to another process to be executed. And as I said, the CPU scheduling is the central of operating system design. And if you have better algorithm for your CPU scheduling, you have more efficient machine. That we will discuss it. So, CPU input-output cycle. As you see here, guys, we have CPU burst, input-output burst, CPU burst, input-output burst, because this is what happens inside CPU. Always the processes get CPU time to be executed, and meanwhile they've got to wait to get some input from the user or from the other files or for other parts. So we run some processes, we wait for input output, we run again, wait again to get some input. We do this cycle till we finish that. And then the program is finished and we need to terminate the process. So this CPU, this cycle happens to the point that this process should be terminated. So the final CPU burst ends with a system request to terminate execution. So this cycle happens till end of the execution. CPU scheduler. Whenever the CPU becomes idle, the operating system must select one of the processes in the ready queue to be executed. So we have someone inside the CPU, which is called CPU scheduler, and his job is to find a right and appropriate process and gives it to the CPU to execute that. Where it gets the process from, it gets it from the ready queue, because we've got two queues, one waiting queue, one ready queue. So this is scheduler's job to take the process from the scheduler, from the ready queue, sorry. The selection process is carried out by the CPU scheduler. The scheduler selects the process from the process in the memory that are ready to execute and allocates the CPU to that process, as I explained. Conceptually, all the processes in the ready queue are lined up waiting for a chance to run on the CPU. The records in the queues are generally process control blocks, we discussed it in the previous lecture, of the processes. So what happens? These PCBs comes to the ready queue, and this is the scheduler's job to choose the right one from the ready queue and execute them. So that's a really good diagram. We had something similar for the threads in the previous lecture, but this one is about the processes and the status. When a process comes from memory, I'll tell you later on how, it goes to the ready status. When it goes to the ready, it means that we need to give CPU time to be executed. So it goes to the running status to be executed. While you're running the processes, maybe you need to get some input from the user, from other programs, whatever. So it goes to the waiting queue. And as soon as it gets the input and the event completed, it goes to the ready queue again to be executed. So that happens always till finish the process, and the process time finishes, and we terminate the process. Or sometimes we are running some processes, but suddenly an urgent process comes and we need to stop the running process, give CPU time to that specific process to be executed. We call it interrupt. So we are running, an interrupt comes, so we've got to take the CPU, give it to the one that we were executing, we've got to give it back to the ready queue, execute that high priority process, and when it finishes, gives the CPU time to that process again to be executed. So this is very important diagram, and we are going to discuss it in more details, that how scheduler works for such processes. So we have two kinds of scheduling. One of them is called non-preemptive scheduling. In non-preemptive, as we see from the name, that we cannot stop the process. It means that here I talked about the interruption. When a high priority process comes, we need to stop. But in non-preemptive scheduling, we don't stop. We don't care about the higher priority process. So we don't stop it. So we don't have this interrupt. Actually, we run it. If you need to wait for something for an input, okay, go to the waiting queue and then go back to ready and then running. But we don't stop. So this is non-preemptive. Non-preemptive or cooperative scheduling decision may take place under the following circumstances. What are those? One of them, when a process switches from the running state to the waiting state for input request, look, there is no interrupt here, or when a process terminates. In these two situations, we use non-preemptive scheduling. Here, in this bit, we go from running, waiting for something happens, and termination. In this algorithm, that when we don't have interrupt, non-preemptive can help us. And as you see, we don't have any choice because the higher priority process are not given any CPU time for it. So when a new process comes, it must be executed, it must be selected for execution if it is on the ready queue. And also, CPU has been when a CPU has been allocated to a process, the process keeps the CPU until it releases the CPU either by terminating or by switching to the waiting state. It means that here, when it goes there, either it finishes the process and goes out, or it needs to wait, goes back to the waiting queue. So there is no choice for selecting the processes, and we've got to stick to the rules of non-preemptive. I'll give you a numerical example for that and you'll see. As you see, it's not efficient because interrupt is quite important. So the very old Windows, like Windows 3X, series of Windows 3, use that. The other one is preemptive scheduling. Preemptive scheduling is when a new process with higher priority arrives, their running may be stopped. Here, again, let me go back to that. We are running some processes, but a very high priority process comes. We need to stop the current running process, executing process, and we need to give the CPU to that process. So we need to interrupt that. With non-preemptive scheduling, we cannot do this, but with preemptive, we can do that. So when that happens, when an interrupt happens, interrupt occurs, running state to the ready state, or waiting state to the ready state. For example, when a completion happens, and one of the processes requested from the input output, when it gets, now it wants to go back to process. So maybe we've got to stop again some of the processes and execute that one. So in that case, we use preemptive scheduling. As you see, we have choices. The whole idea is to give higher priority process CPU time. So we have choices for that. But we need, the difference is that between preemptive and non-preemptive is that we need some specific and special hardware, for example, for timer. For example, we give time to the process. For example, a process has got 5 seconds to be executed, millisecond actually. 5 milliseconds to be executed. If you see that in this process, the time is taking more than 5 seconds, you need to stop that and give another process CPU time. So we need specific hardware like timer for preemptive scheduling. And at the end is that most of the all the operating system at the moment, they are using preemptive scheduling. So we're talking about the scheduler. I said that schedule is very important because it chooses the right process to be executed. Schedulers are a special system software. They are software which handle process scheduling in various ways. Their main task is to select the jobs, the processes to be submitted into the system and to decide which process to run. So it's the brain in the operating system who choose the right process to be executed. We have 3 types of schedulers: short-term, medium-term, and long-term. What's the difference between them? Long-term scheduler is for the big programs. For example, you have multi-programs and you want to make them ready to be executed. So this is a long-term scheduler. Okay, you have ready queues, you make the queues are ready to be executed. So this is the decision for the long schedule, that how many processes will stay in the ready queue. They decide on the degree of the multi-programming systems. It's a bigger picture, let's say. Medium-term scheduler, it's, as you see from the name, is for the middle term. Most often, a running process needs input-output operation, which doesn't require CPU. Hence, during the execution of a process, when input-output operation is required, then the operating system sends the process from running queue to the waiting queue. When a process completes its operation, then it should again be shifted to the ready queue. All these decisions are taken by the medium term. As you see, we are somewhere between short term that immediately should be executed and the long term that we are talking about the big picture. So from waiting queue, a process goes to the running queue because again we are a bit far from the CPU to be executed. To execute that process, we use mid-term schedule. The most important one, that this is our main focus, is short-term scheduler. For the short-term scheduler, when there are lots of processes in the main memory, initially all are present in the ready queue. We are talking about the now. Which process should go to the CPU now? So we need to choose from those. For example, 4 processes are coming to the ready queue. They are in the ready queue, and they want to get some CPU time to be executed. You need to choose one of these 4 to be executed first. So we need to use short-term scheduler. So dispatcher. Dispatcher is another program we have inside operating system. What does it do? We discussed about the scheduler. That scheduler tries to find the right process to be executed. But okay, it chooses, for example, between 4 processes. The first one should be executed is process number 2. It defines the right process. Who does that? That's dispatcher job. So this is dispatcher job, that function that after selecting the process, take it from, for example, running to the ready state, it takes it to the running state. So after scheduler, dispatcher comes and does the job. So dispatcher is the module that gives a process control over the CPU after it has been selected by short-term scheduler. That's important. What are the functions? Context switching, switching to user mode, and give the right place for the program. We discussed context switching in the thread, but that one is a function of dispatcher. Switching to the user mode, if you remember, we have user mode and the kernel mode. So I'll go back to that quickly. And give the right place to the program. Jump into the proper location in the user program to restart the program. So these are the main jobs of the dispatcher. And once the dispatcher has selected process from the queue, the dispatcher comes into the picture. So again, after scheduler, the dispatcher comes and does the job. And it is the dispatcher who takes the process from the ready queue and moves it to running queue, running state. So just we discussed kernel and user mode, but here again, if you want to actually refresh your mind, in the kernel mode, the executing code has complete and unrestricted access to the underlying hardware. And in the user mode, the executing code has no ability to directly access hardware to the reference memory. So as you see, this is the dispatcher job, can take one process from the kernel mode and gives it to user mode, that it doesn't have access to all the hardware. So dispatcher can actually move between different modes of operating system, which is the kernel and user. So scheduling is very important. I'll tell you how it works. But we have a couple of criteria for scheduling. CPU utilization. We need to keep the CPU as busy as possible. We don't want to have idle CPU. Throughput. Number of processes that complete their execution per unit of time. Turnaround. This is very important. Turnaround time is the amount of time to execute a particular process. As you see, exit time minus arrival time. When the process comes till it goes, that time called turnaround time. The other one is waiting time, the amount of time a process has been waiting in a ready queue. Turnaround time minus the CPU time or burst time. This is called waiting time. And the last one is response time, the amount of time it takes from when a request was submitted until the first response is produced, not the output. Among them, these two are very important, turnaround time and waiting time. So what is a good scheduling algorithm? A good one is the one who makes the CPU utilization maximum, minimum CPU idle time, maximum throughput, maximum number of processes to be executed, minimum turnaround time, minimum waiting time, and minimum response time. Very quick with maximum capacity. If you have an algorithm that can do this one, actually maximizing the capacity and minimizing the waiting time, let's say turnaround time, response time, that's a good algorithm. So we have 6 algorithms. 2 of them, the first 2, I'm going to discuss in the second part of the video, and the next ones, the next 4, in the next lecture that I will provide for you. So thank you very much. Let's go to the next one.